Hi,
Hi,
hi Mrinal, how are you doing?
very good, Anish. Good to see you.
We'll wait for some more people to join in, so I just start.
Okay, great. How many have joined in as yet?
I see like 23 people have RSVP, so let's see if other people join in. Let's give them 5 minutes so everybody can join in.
Absolutely.
How did you find the URL?
You just posted something, I think a minute back or something,
Yeah, yeah,
and it just came up
yeah.
exactly a minute ago. So that's how I came in. I find your class really exciting. Thank you very much for hosting it on this way.
You're most welcome. So, what are you? You can introduce yourself if you want, since we're waiting.
Okay, so I work with Intel actually as a RET engineer, and
Okay.
I just got done with my PhD a couple of months ago from Michigan Ann Arbor.
Well, congratulations.
Oh yeah, thank you.
See, you're in the Portland area.
That's right.
Okay, okay. Yeah, summer in Portland can be quite good. That's what I've like
Oh
summer is
yeah, yeah. Actually, after Michigan, everything's good.
I guess yeah.
This winter was especially miserable. So, or just too cold.
Yeah, yeah.
So, do you work at Applied Materials or do you work at Stanford, or do you like shuttle between both?
Between both. So, I work at Applied Material. I teach at Stanford mostly. So I teach like a couple of classes. There's one related to the one we are studying here. And then there's another one on solar that I teach, and then another one on semiconductor devices basics. So, yeah,
Okay.
somebody else who joined in too. Hey, Kwadwo-san.
So, has your PhD was it also in in semiconductor devices, or was it more in material science?
It was more in semicon. It was kind of at the interface of material science and semiconductor devices. So I was studying these two-dimensional whole gases in 3-5 quantum ways, and
Okay.
it was very interesting. Like, holes is in general, it's a very fascinating topic, right? It's like an absence of electrons, and
Right.
we used to like cool these small quantum wells to very low temperatures and apply very high magnetic fields. And then all of a sudden, like a lot of things that you study in quantum mechanics, you start to see them experimentally. Like the resistance of the material, it starts oscillating. So it was very fascinating.
Okay. Okay. It's quite fundamental.
Yeah, very fundamental. What did you work on?
My work was on density function theory, so doing really large scale DFT calculations, and we were trying to come up with really highly scalable algorithms for the same. and which is what preventing most of the existing commercial codes from working really well, is that they don't scale well. And so that was my, and then we applied it to, of course, material science problems like uh, estimating like mechanical properties of crystals to a good degree with just simulations.
Okay. Okay. Yeah, DFT is very interesting. I hear it was like started in the chemistry domain, then it got adapted to.
Yeah, exactly. And by the time it's at material science, it's just that the larger you can do it, the better, the more accurate you can be in your predictions. And,
Okay.
and right now it is quite inaccurate, or it's accurate in certain places, but not accurate for everything. But then it certainly looks like size is the limiter. And then if we can push the size as people are also pushing accuracy, both put together will can actually start having impacts everywhere.
Nice, nice. Do you work on DFT at Intel too, or you work on?
Oh no, I work on something you touched upon in your lecture, which is resolution enhancement techniques.
Oh, okay. Okay. There was this guest lecturer we had from Intel, actually maybe 2 years back, Sam Sivakumar.
Oh yeah, yeah, yeah. I bump into him in the elevator.
Oh, okay. Okay. Yeah, you can tell him that, his lecture is part of the course. He can forward it to other people. Or you can
Yeah, I
also.
told him that I saw him on YouTube before I saw him in reality, so I was like laughing about that.
Okay. We have 12 people who are watching, but they can't join for some reason. I can't imagine. Let me post the link on YouTube as well if people want to join.
Sure, absolutely. So are you traveling a lot this summer, or is that all out of the window?
This summer, no. No, I'm not traveling much this summer.
Okay.
Partly running this course.
Right, 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 right. So there is someone I can see.
Yeah, hi, Professor. Can you hear me?
Yeah, hi.
Hi.
Chintamani, how are you doing?
Yeah, hi.
अरुण तेरे
Good, good.
के माइवन कब आप
Do you want to
So
introduce
it's a very
yourself?
interesting course, and
माइवन में आए
yeah. So I have a background in circuit design. I have been with Intel actually, and
MAIWAND माइवन कब आप
Okay. Actually,
મને એકલો વેબ કોલ છે હું અટેન્ડ કરું છું
if you can like mute your microphones,
વાગે
if you want to speak, guys can mute your microphones unless you want to speak, so we can hear one person at a time. That would be great. Hi, Jalpa. Hi, Mark. How are you doing?
Hello, hello, from La Crescent, Minnesota.
Nice. Do you want to introduce yourself?
Yes, I'm I'm actually taking this course purely out of interest. I'm not an engineer at all. I'm actually a radiologist. I work in a medical center here in La Crosse, Wisconsin. But I'm completely fascinated by technology, and and this course has been great so far. So I'd love to hear some further insights from you today.
Awesome, awesome. You know, my sister, brother-in-law, they're both physicians. My mom is a physician too, so I'm kind of like the only engineer in the family.
And what? I'm sorry. What kind of physicians are they?
So my sister is a nephrologist.
Okay.
My brother-in-law is an intervention cardiologist,
Uh-huh.
and my mom is a gynecologist. So
Oh, well, there you go. Lots of
yeah,
professionals hanging around, huh?
yeah. So I see there's a lot of like lovely nature in your background. What is that?
Well, I live. I work at a very large medical center, but we live on 160 acres, 15 minutes from the medical center, which is kind of like our little play heaven, you know. So we live in a small town, but yet we live near a big medical center. So it's kind of the best of both worlds for us.
Nice.
Yeah, yeah.
Seems looking out the view from your window, it seems like a nice place to be.
Yes, indeed it is. But I'm sure there's lots of advantages where you live out there too.
Yeah, but I don't have that view for sure.
No, no.
Okay. Hey, Quadro, good to have you back.
Yeah, hello. Nice to see you again.
How was this week's content, FinFETs and...
Oh, okay, I've not been able to have a look at the video, but I'll do that after this hangout. I was a little bit busy with my research, so I'll have a look at it on Sunday here.
Okay, all right. Hey, Jalpa, are you there?
Can you hear me, by the way?
Yeah, we can hear you. We were able to see you before too.
Yeah, actually, I'm just outside, so like having call on my mobile, so just kept that invisible mode.
Okay. Yeah, I've seen you're pretty active on the forum, so that's pretty good.
Yeah, thank you. Actually, I'm working upon particular project for kind of creating a grating design on contact lens surface, and I'm pretty much new in this field. So for me, like manufacturing thing, nano material layering, different processing technology, everything is new. So I'm really enjoying the course, because I'm getting practical input from the course itself. So it's going pretty well for me.
Okay, awesome,
Yeah,
awesome.
thank you. Actually, I'm working upon particular project for kind of creating a grating design on contact lens surface, and I'm pretty much new in this field. So for me, like manufacturing thing, material layering, different processing technology, everything is new. So I'm really enjoying the course, because I'm getting practical input from the course itself. So it's going pretty well for me.
Awesome, awesome. Good to have you.
Actually, I'm working on particular project for kind of creating a grating design on contact lens surface, and I'm pretty much new in this field. So for me, like manufacturing things, material layering.
There's some repeat, somebody is like watching it on YouTube and it's repeating.
Right. It's just...
I don't know where it's coming from. Hi, Varada, how are you?
Hi, Anish, doing fine. How are you?
Good, good. You want to introduce yourself?
Yeah, I first of all want to thank you for this course. It's an excellent course to give an overview. I did work on computational lithography in patterning actually, so I'm exposed to this RET and other processes, but your course is giving me a really good foundation and expanding my view in a sense.
Awesome,
Good.
awesome. Where do you work now?
Actually, right now I'm in between, so I thought I should make use of my time. Course came up, I was really interested in doing it.
Yeah, awesome. Yeah, like a lot of MOOCs, they're like most helpful for people who are like in between jobs. They can pick up new skills and then
Yeah.
use them for their interviews. And so, good to have you. And hopefully that should help in your next gig where you happen to go.
Yep. Thanks. And I was wondering at the end of this lecture, could I ask you a few questions on that FDSOI? Because
Yeah,
I'm
so
familiar.
sure. Yeah. That's
Yeah.
that's the topic that we are discussing this week anyway, related to FinFETs and other like modern transistor technology.
Right.
So yeah, go ahead, go ahead. We can start, in fact, with your question.
Yeah, my question was, I mean, it's at a very basic level. I've been going through how MOSFETs actually work, the physics behind it, and I want that partially depleted and fully depleted explained to me much better. I understood the current and voltage characteristics that you drew and the effect of voltage and how people want to uh, kind of control better with the gate. But what is the exact difference? I was also listening to one of the lectures by, I guess, the Berkeley professor who started FinFET,
Yeah,
and
Cheng-Ming Hu.
yes, Cheng Ming Ho. And the one point I picked up from him was he says that it's very essential that the fins or whatever you call it, fins have to be extremely thin. And basically, it's not so much about fins. It's like thin film technology, which was not available to them when they started it. So they rotated the structure and made it standing, and so made it a 3D kind of stuff. So how, I mean, how thin does it have to be, and what is the physics behind it being able to control? And I didn't get what fully depleted means and what partially depleted means there.
So fully depleted means that, let's say I have, like this fin, and if my when I'm turning my transistor off, right, it's
Yeah,
able to like completely deplete this fin or this region of all electrons. I mean, if you have a little more background in semiconductors, there's a concept called depletion width.
yeah,
Okay.
yeah, yeah,
So if the thickness of your channel,
yeah,
right,
yeah.
it happens to be less than your depletion width, then you say that, your device it's fully depleted. So like you have this fin and if my depletion thickness happens to be this much, when I try to turn it off, right, it would be fully essentially depleted and there could be no current which can pass through it, in another region. The whole fin would be depleted of any carrier. So that's what you call as depletion width. That's what you call as fully depleted devices. So in a SOI device too, if you make the thickness of this device, if you make it thin, let's say your depletion width, which is determined by doping, is fixed, okay,
Okay.
and you try to so Jose, if you can like mute your microphone, you can turn off the YouTube channel now. You can be, you're in the Hangout. So if you want to turn off your YouTube channel because there was some disturbance coming. So okay, so coming back to your question, Varda, if this is my depletion width and this is the thickness of my channel, as soon as it starts becoming comparable or less than the depletion width, then I call that device a fully depleted device. And from a current voltage perspective, if that device is fully depleted, then my subthreshold characteristics and my off characteristics of the transistors are much better. I can completely cut off the leakage. So that's what means by fully depleted. And I think what Cheng-Ming Hu was saying might be correct. Like when he started researching on these FinFETs and SOI transistors back in like late 90s or early 2000, right?
Right.
That time the SOI technology which was available, the channels were not as thin maybe, but currently you can buy like a wafer which would have a film which is 5 to 6 nanometer thick, and very uniform, like with a uniformity of plus minus 3 angstrom throughout the whole wafer. So I guess yeah, when that if you, at that time if that technology these very thin SOI wafers were not available, it would have made sense to kind of etch and make a fin. Okay.
Okay. So partially depleted is basically that the film was not thin enough.
Yeah, partially depleted means the depletion width of in that wafer is essentially bigger than the thickness of that SOI film. So that's what it means.
Okay.
And partially depleted technology is also used. It was used both by IBM and Global Foundries, uh, but it does not give you as good electrostatics as a fully depleted device. Okay.
I worked computational lithography in IBM just the last year.
Okay. In Fishkill or?
East Fishkill.
Oh, nice. Okay. I used to be in that area 2007 or so. Yeah. So I'm
Okay.
very familiar with that area.
Okay.
Yeah. Hey, Jose.
He's on mute.
Let me on.
Okay.
Okay, we can take more questions. Whoever want to, go ahead. We can take some more questions. I have some models of things with me as well. So if you want to refer to it, I can.
So I have a question. This concerns with the introduction of fins. You have like far more flexibility in your contacts, right? You need not be always going straight up. So you can route them in different ways. So how does it have a big impact on the architecture in the ways you design stuff?
So you mean like if you have a fin, you can place a contact not just here, but it could wrap around the whole fin, right? Is that what you're saying? Or?
Yeah, I mean, it could go up and I mean, even the gate contacts, right? The gate contacts could come out horizontally and then move up, and there could be so many ways of even getting the gate contacts up. And then is that does that affect the architecture in a big way, or does that give you far more flexibility in architecture terms too, not just the processing terms?
So there are like uh, quite a few implications of that. One is that it can now wrap around the whole structure, right? So it can go, the contact can like wrap around both the gate contact and the source drain contact can now wrap around the fins, right?
Okay.
Uh, so that gives you more surface area with the fin, right? The contact has now, more surface area in touch with the fin. So in terms of contact resistance, if you can achieve that conformal contact, right, it would be better. But at the same time, like people who actually make processes or equipment for doing these stuff, right, it suddenly becomes more challenging for them because you need like more conformal deposition throughout this fin, right? So anything which is like line of sight process, right, would not work well because now if it's a line of sight process, it would just cover on the top, not on the side. So you need more conformal processes. So as things go to 3D transistors or 3D even NAND, which we'll be studying next week, you need more and more conformal processes. Like you need processes like ALD and CVD increasingly more to make contacts both on the gate and on the source and drain, right? So
Right.
that's one implication of it. There's a negative implication which is in terms of parasitics as well, because if you have these 3D contacts next to a 3D gate, the coupling between these two happens to be more as compared to what it was in a planar device. So there are some implications which are, in terms of parasitics, etc., which are not good. So that's
Okay.
it. I mean, there are advantages and there are disadvantages.
Okay.
In terms of architecture, like it does. You can make now trench contacts. So like it's something that you might be familiar since you work at Intel. That initially you used to have one individual contact to each transistor, but now you do it in a trench. So that's one new implication, which has partly come because of lithography. It's easier to pattern trench.
Right. And then second and last question is when you're doing like ALD on such small scales, right? Talking about a couple of tens of angstroms at the most, or a few nanometers. What happens to defects in the materials? You're going to have all sorts of stacking faults and everything else. I mean, then these can destroy performance, right? How do you ensure that the crystal remains perfect in your active region?
So when you do 3D devices like these fins or even 3D NAND, I mean, whenever you have these fins which are, structurally they need some TLC always, right? So you can't be, so one of the precautions that you do is you do a lot of your processes at low temperature, right? So you don't damage or essentially deform the crystalline material in the film, right? So a lot of the processing that you do, you kind of ensure that you don't damage the fin, and a lot of it has to do with like doing low temperature processes, and also some of it has to do with like increasingly getting rid of wet processes, right? So especially if you have these 3D structures and if you do a lot of wet processing, they can fall. So that's another thing that we increasingly see that you try to get lower in temperature and also try to move to drier processes.
Thank you.
Okay. Okay. Any of you guys want to shoot ahead with the next question?
Oh, this is Mark. I do have a question that may not be directly related to the issue at hand. I haven't listened to this week's lecture yet, but this may be a very simple question, but I'm not understand why there hasn't been a strategy with chip manufacturers to start building, in 3D. In other words, create multiple layers. What are the limitations to doing that? Is heat the limiter, or is it just laying additional layers? The physical laying of additional layers on top of other layers is the limitation. What are the challenges or limitations of doing that?
So if you segment it among memory and logic, right? Logic, it's slightly more difficult because you have not just transistors, but you have these interconnects which go between them, right? So not only you have transistors, but you have these multiple layers of interconnects on top, right?
Right.
So, but if I think about memory, it's a little more simpler because I have a more Can you guys hear me?
Yeah.
Mm-hmm.
Yeah.
Okay, I don't know what happened to my camera.
No, you look fine. You're fine.
Oh, I'm fine.
Yeah.
Okay, so but if I have a memory structure, right? I can essentially have
We are looking at we're looking at the front of it now.
Okay, all right. Okay, I can't see myself, but if you guys can see it.
I see.
Hey Jose, there's something wrong with your mic, so if you can you are either playing YouTube, so if you can stop that one since you're part of the Hangout now, then I can unmute you and you can speak. Okay, so Mark, coming back to your question, like it's easier to do in memory where you have like these bit lines, word lines stacked on top of each other, right? So and it's a very regular set of interconnection between them, right? One of the reasons that So 3D memory has been talked about since a long time. I think the very first company that did this was something called Matrix Semiconductor back in 2004. So they made like a 3D one-time programmable memory. Now, increasingly, the NAND manufacturers, since they cannot scale the cell anymore, right?
Right.
We'll talk about that more next week when the topic of discussion would be flash memory. So they can't scale their transistor anymore. So the only way left for them is to go vertical, put multiple of these stacks on top of each other. Okay. It does give you some advantages, like you can relax your lithography, so you can use like an older generation lithography because you don't need to make structures as small. You can stack multiple of them on top of each other. Okay. The problems that arise are there are quite a lot of them. One of them is like when you stack these multiple layers, how do you then subsequently etch them, form these structures? So again, it requires very conformal processes. Okay. There are other challenges in terms of parasitics, especially if you have a memory. Again, it's okay if you don't understand it right now, but it's difficult to select like one cell, but not select the cells which are adjacent to it. Okay, like if you have a 3D structure, there's this complex interconnects of bit lines, word lines, lines interconnecting these cells. If you select this line and this line, right, one line
Right.
and another line on top of it, the cells which are next to it, which also see some voltage, right? I mean, there are 3 cells which are in series to it, which will also see 1/3 of the voltage across them, right? So like those things become important, like uh, controlling your parasitics, selecting one cell at a time, right, from a device perspective. Then from a processing perspective, how do you deposit these many layers and etch them, make these 3D structures? But we are starting to see that, in fact, if you want to jump ahead a week, Google this thing called Samsung 3D NAND. So Samsung, for example, last year it announced this flash memory chip, and it stacks like multiple of these cells on top of each other. So, I mean, you're ahead of the curve here. You're definitely thinking on the right direction. You do need to go 3D to, achieve the kind of performance. It's not going to come from planar scaling. You have to stack these things on top of each other.
And heat is going to be a significant factor there, because I mean, the heat's a big deal now. If you put twice as many transistors, one on top of another, I think might even get worse or not.
Yeah, heat and all those things are going to get even worse. Like even now, when you put a memory chip on top of your processor, which happens in all your iPhones and smartphones, right? It's already a problem, and we will talk a lot about that when we talk about packaging. It's a big problem. So, you're kind of covering my content from 2 weeks. And we will get to that in a lot more detail like 2 weeks from now.
Oh, great. Good deal.
Yeah.
So, Professor, actually I have another question with respect to the memory. Is hybrid memory cube the same that you were initially talking about?
No, hybrid memory cube is you have these DRAM chips, and they're thinned down, and then you stack them on top of each other, and you use these thing called through silicon via, which is something also we will study in week 6. So hybrid memory cube is not the same as 3D NAND that Mark was talking about. So hybrid memory cube is you have these DRAM chips, and you essentially thin down the die and just stack them on top of each other. Okay, so it's a memory cube where you just stack individual chips on top of each other.
And with respect to your initial discussion for 3D, you said that there are select lines. I understand what you're talking about. Shouldn't there be 2 select lines for the 3 stacks for 3D, or is there like I mean, I understand one vertical and one horizontal line, but for the vertical line, shouldn't there be 2 of those instead of 1?
Yeah. So you're saying if you have a 3D structure, you need more than just a bit line and word line, right? You need
Correct,
like
correct.
select line. So yeah, there's another uh, select line which runs on the top of these, which selects like a particular section. So there are more than just a simple bit line and word line. There would be 3 selectors needed. You're right.
Oh, thanks.
Okay, at least 3 selectors needed to select one particular cell. Hey, Qualo, how are you? You're very quiet today.
Yeah, I'm online trying to read about FinFETs and to get more information about it since it's quite new. I'm working on energy storage devices and it's quite new from the things I'm used to and the things I know. So I'm currently reading, I just Googled FinFET and I'm just reading about it to find out a question or something interesting to ask and to contribute to Hangout.
FinFET in general is not that old as such. Like, you know, Mrinal can speak to it, but it was introduced like in 2011 at Intel. A lot of the rest of the companies are like still introducing it. So it's a very new topic, and you know, it's a very fascinating topic too. So, and it's very relevant. Like if you go to any big semiconductor company, like you know, TSMC, Samsung, Global Foundries, they're all like right now are taking FinFET into production. So it's a new technology, and you know, it's very relevant, very pertinent, especially if you want to, you know, start your career in semiconductor industry right now. It's very pertinent to learn about it.
Okay.
Okay. So, you know, I would like to put a plug-in regarding the project as well. And if, you know, it's a very fun project. When I do this class at Stanford, people, the students, they really enjoy it once they make a screencast video on their own, and especially when they review other people's video and, you know, you grade your peers' work. It's like very fascinating. So, and it should not take you a lot of time. Like I've posted on the website a lot of apps. If you have a tablet that you can use to make a screencast video very fast, and also if you have a PC, how you can do it. So, you know, I strongly would recommend you to, you know, go take a look at it. Do the project. I might extend the deadline for it for a week because few people are still having some technical difficulties in doing that. But you would see like the breadth of you know, the learning that comes across, not just by listening to my videos, but like making a video of your own, and also especially when you review other people's videos and, you know, try to give them scores based upon the technical and the creative content that they have produced. So it's very nice. So please do it, and it should be fun. I can guarantee you it will be a lot of fun.
Just a small plug for the Mac users, because I just fell upon this. You can actually use QuickTime. Just open up QuickTime and you can create a screencast very easily. You just go to File, New Screencast, and it's very simple. So you don't need any apps or anything.
Oh, okay.
Thank you.
Sorry?
Thank you.
Oh, all right, just for you Mac users.
Okay. I might post it on the Mark. If you like, send me an email or send me a link. I'll post it on the class website as well.
Oh,
Or,
sure.
Yeah.
Yeah, I have a. Yeah, I'll find the link. I'll send it to you. Yeah.
Okay. All right. You guys want to ask any more questions, or yeah? We can do it on this week's content, but we can do it on anything else related to the class as well.
Well, I don't want to hog the show here, but I do have a question about the glass. I was going to do a little screencast on Gorilla Glass versus sapphire glass and their properties and so on and so forth. But one question I have is I wondered, could you, in order to, you know, because they're always racing to make things thinner and thinner, would it be possible, technically speaking, to sort of somehow etch the, you know, the display right onto the glass? In other words, create a very flat, you know, piece of sapphire glass or Gorilla Glass, and then lay down silicon on top of that, and then etch your transducers on there so that you wouldn't have two layers. If I'm not mistaken, you have two layers now. And could you do that possibly, or that's too technically difficult?
Yeah, so first of all, I mean, that's an excellent topic for your project that you've chosen. I'm sure the video will come out to be very nice. Since you're talking about it so passionately, I can already imagine the video would be.
Well, I don't know. I'm going to try. But
Yeah. So currently what you're saying is, like, can you make your transistors on the glass itself too, right? Like, instead of making so okay, let's take it like, let's talk if you can do it in for OLED transistor first, because they're simpler, right? They have less layers. Let's think in our mind, can we do it? So right now what they use, there's something called in-cell technology. Okay, so what that does is it prints your touch screen directly on your glass. So the capacitive sensor, right, in the touch and all, those are nowadays actually integrated onto the glass. So instead of having two layers, it's just one layer. So you are right. Like, I mean, they already are, like, earlier it used to be a touch, then a glass, then your liquid. If it was a liquid crystal, then your filters, and below that a TFT backplane, right? But at least now, I think there was a question on this in the display week. Like, you have integrated now your touch onto the glass as well. If you now think of, like, integrating your OLED also on top of it, right? And you're essentially, like, what you're saying is, like, you etch grooves and fill your um, organic material which makes up the LED into that, right? And
right, into the sapphire or the Gorilla Glass. Could you do that?
you could do that, and let me see. One of the thing that you might have to be careful about is to protect the capacitive module that you have put in, right? Because that's already integrated onto it, and that's probably, you know, already that glass is already processed on one side, right? So now when you're processing it the second time, you have to kind of make sure that you are not damaging that touch interface, right?
Yeah.
In terms of thickness, would you get any advantage rather than just making that LCD? You probably could, yeah. So it's a neat idea. I don't know why people don't do it. One of the reasons could be, like, since you're putting your touch screen already on it, and then you're putting your LEDs onto it, it might be difficult to protect that. The yields might go down, right? Currently, if you separate it and then you combine it, the yields are higher.
I see. Yeah.
In terms of thickness advantages, you probably could get some thickness advantage if you make it directly etch your, you know, LEDs, put them right in the glass itself, right? Yeah, it's a neat idea. Yeah, not sure what exactly is preventing it. It could be a lot of things. Like, it could be a thermal budget limitation. It could be just a yield/cost issue. It could be something else.
You said thermal. You mean, in other words, some things wouldn't tolerate a higher temperature, and other things require a higher temperature.
If you make transistors, right? especially your TFT transistors.
Yeah.
Transistor processing is typically, it involves temperature when you put the gate oxide, when you put the source in it, right? So it's a higher temperature process.
Okay.
Yeah.
Okay.
That's why it's even difficult to do it on like these flexible substrates, right? So especially if you, that's why they move to these newer materials, zinc oxide, low temperature polysilicon. It's difficult to do even the TFTs on a sheet of plastic, right? So you need the way a lot of them currently do it is they make those TFT layers on a more a substrate which is like more tolerant to these temperatures, and then you transfer it over to your uh, layer which has the rest of the OLEDs and so on. So that's another issue that might be. Again, I'm speculating.
Yeah,
I
sure.
have
Yeah.
not like looked into it in more detail, like why, but it sounds like in theory, at least an idea worth exploring.
Uh-huh.
My friend, how are you? Jose? Unfortunately, some issues on this side, so unfortunately I have to mute him. Okay, Binal, you just joined in. How are you? Okay, any guys, any more questions on the class in general? It doesn't have to be related to this week's content.
Yeah, I have another question if nobody else has any. Uh,
Go ahead.
this is not with. I remember you mentioning in your very first class how 90% of the iPad is just the battery by volume. And so, will any of these techniques, nano manufacturing techniques, help in? Like, so, what are the issues holding back scaling down of batteries, and where do these kind of manufacturing techniques do they have a role in aiding that, in helping scaling down battery sizes?
Yeah, batteries is whole. It's a very interesting and a very deep topic in itself. To give you like a 5-minute summary of it, uh, the battery also it progresses. It has an exponential law like Moore's law, but the exponent is not as big. It's 8% per year rather than 33% per year like Moore's law is. So battery capacity does increase like 8%, and kind of it is limited. It's limited by the capacity itself is limited by the chemistry, right? So if you think about, they've moved to like lighter and lighter and more dense chemistries. Like it has moved from nickel to lithium, but you can't think of like anything more higher energy density in terms of going beyond that. So it's kind of stuck at lithium polymer for a long time, and they're evolving it slightly every year. So it does go up by like 8% every year. But it's a slower exponent. It's there's this great theory about like exponential technologies, and you should typically try to get into technology which have a higher exponent. It just evolves much faster. But battery do evolve, but at an 8% exponent. In terms of like charging and discharging of them, can you do it faster? So a lot of like innovation is happening here. People are introducing a lot of like nanotechnology related techniques, like making electrodes not just flat but making them in a nanowire fashion so they can charge faster. They can again, I'm not all current on it, so I can't like speak on it authoritatively, but like using nanotubes, using nanowires to improve the charge discharge time. In terms of energy density, that is the evolving side. It's at like 8% per year. So even if nothing is like an electric car, if it's like 2000, if you bought a Tesla in 2011 versus if you buy it in 2015, the battery uh, capacity would have come down by the battery price would have come down by 30%. And you know, uh, the battery, it's not just an issue for these small mobile devices. It's also an issue for like electric cars, even a bigger issue for electric cars, right? So they're again trying to push it, but it's just at a slower exponent. So last hangout somebody was mentioning about like can we use supercapacitors? So again, it's an issue to get them at this smaller size and at a price point so the whoever invents it, right? It's like would be an instant multi-billionaire whoever solved this problem, because it's like one of the most pressing problems. Uh, so I've seen like people trying to do supercapacitor. I've seen like these guys trying to make like small fuel cell, which would go in a this company based out of Austin, which is trying to make a small fuel cell which powers your cell phone. So again, like it's one of the biggest problems. Like we've done a lot in terms of Moore's law, but not enough in terms of battery. You know. Wireless charging might come to like give a temporary respite where you can charge these things wirelessly instead of like putting the card every time. So that might give some temporary relief. But increasingly, you know, like when I was testing wearables that we'll talk about in week six of the course as well, right? It becomes even more problematic. Like there, the energy requirements and the the power consumption requirements are even more tighter. Like any of you who has used a wristband, like a Jawbone or something, right? You don't want to charge your watch every day, right? At least I'm not used to it. Like, maybe I will. I was not used to charging my phone every day too, but now everybody does it, right? So, but again, it's a big and very pertinent problem. We haven't touched upon it in this course, but do explore it more. Like it's again, I can't speak to it too authoritatively, so I'm just giving a general overview. Okay.
Thank you.
Just a question about the fuel cell. Do you have a rough idea as to whether like the energy density at current state today of a lithium cell versus a fuel cell, whether the energy density given the same weight would be more with a fuel cell versus the state-of-the-art lithium battery, or whether that's not equivalent? Do you know roughly?
Yeah, so again, it depends upon. I mean, I've seen the fuel cell companies do make comparison with this. Say, it's at least like few times higher as compared to what you get in a state-of-art lithium polymer or lithium based battery, right? So, lithium plastic based battery. So, yeah. So I've seen claims which claim, like. Again, these are coming from people who are pursuing it, so you have to analyze it with your own, grain. You take it with a grain of salt.
Grain of salt,
yeah.
Much higher. Yeah.
Okay.
I have a question.
Yeah. Go ahead.
Yeah, I'd like to ask. I know that with the FinFETs, we can take advantage of maybe the power, the performance, and area benefits, as compared to the planar FETs and the MOS FETs. But I want to know if there are any challenges facing the design of FinFETs, if there are any challenges that prevents or limits the design of FinFETs.
Oh, there are several challenges, like, in terms of processing of these, it's very complex. Like, you have to make these fins, these 3D devices, prevent them from falling all over, and it just, even for the companies which have been doing it for, like a generation, but even them to go to their second generation, it's challenging, right? So it's very difficult to make it and scale it from a technology perspective. Other things that you'll discover in the videos is that things like parasitics, getting multiple voltages, getting multiple threshold voltages becomes very difficult. You also can't have like a random width, like especially people who make analog circuits, they want, they prefer hand drawing layouts sometimes. I know a lot of analog designers who just draw these handouts by hand. It's more of an art than science, and they cherry pick the width they want, and they're so used to like designing it as they wish that suddenly when you give them something like this, you tell them, hey, you can only have one fin or two fin or three fin, right? So you can have only the width that is the width of the perimeter around this fin, and you only can have that in integral multiples of the number of fins. You can't have like 2.5 fins or 2 3/4 of a fin, right? So suddenly, like, their life becomes much more challenging. Now they can only select their transistor widths among these options, which are multiple times the number of my fins, right? So there are other these kind of challenging as well. So not everybody has not everybody loves FinFET. A process engineer might love it, or uh, semiconductor process technology guy might love it, but when you give it to like suddenly a circuit designer, like he is scratching his head all over and saying, like, what the heck did you give me now? Like a big paradigm shift for him, right? So
Okay.
that's we touch upon that in this week's video. So when you look at it, we touch upon some of these issues over there.
Okay. And also, I'd like to comment about the lithium-ion batteries and supercapacitors and fuel cells. Yeah, I think since I'm working on supercapacitors, and I've also read about lithium-ion batteries.
There you go. So you can speak to it.
Yeah, I think the main advantage of a lithium-ion battery over a supercapacitor is high energy density. But because supercapacitors, they have higher power densities than lithium-ion batteries, and also with the supercapacitors, they can charge very faster. You can charge a supercapacitor within seconds. But now with the research, we are trying to increase the energy densities of supercapacitors. And also with lithium-ion batteries, you see the reaction is a chemical reaction, so it's very easy for it to catch fire. But with supercapacitors, we store the charges on the surface. If it's a carbon material on the surface, also with the metal oxides, but as a result of its redox reaction. So with that, it's very, very safe, and it doesn't catch fire. So I think if we're able to increase the energy densities of supercapacitors, they serve as a better option to be used in that's with the electric cars, since it doesn't catch fire or set up fire. So that's the main advantage of the supercapacitor.
Okay, okay.
What are the disadvantages?
The disadvantage of supercapacitor, firstly, is the energy density is very low, and also is expensive. For instance, there is this material, ruthenium oxide. It has very high specific capacitance, but it's very, very expensive. So we have to look for less expensive materials like iron oxide, manganese oxide too. But they have very low specific capacitance. So by using nanotechnology, for instance, nano wires, nanotubes, nanorods, getting a better morphology, we can get better properties. So that's the main disadvantage of supercapacitors.
Okay, okay. All right, awesome. So I have a few questions which were posted on the event page. Let me answer that. Siva, if you're online.
I'm online.
Okay. You want to ask your question?
Yeah. The question is, one is about the gate technology. So people used to use metal gates, and then they moved to polysilicon, and right now they came back to metal gate. Could you explain a little bit why they moved to polysilicon and then came back to metal again?
Yes, so they came back to metal again because there was I mean, a lot of, from like, I would say from 80s all the way till 2007, the technology was, instead of a metal gate, you would have a polysilicon gate and an oxide and then your silicon, right? The reason they moved to a metal gate was this polysilicon gate, it used to get depleted, okay?
Okay.
And that was adding to the something called the effective oxide thickness, okay? So your short channel effects would be worse because of, you would be depleting your gate material, okay? The other reason which really caused this triggered this move to from polygate to metal gate was the introduction of high K technology. Okay, so if you have a high K material as your gate dielectric, a polysilicon on top doesn't work well. So there's a reason for that. Like there are phonon interactions which happen between the two.
Is
And
there anything to do with the interface?
sorry.
Is there anything to do with the interface? Interface between the metal and the oxide?
So the interface is between this high K and the poly. Okay, and from what I remember, again I haven't refreshed it in a long time, but a poly with essentially, if you put a poly gate on top of a high K, which is on top of a silicon transistor, right?
Mm-hmm.
The mobility of the transistor turned out to be much lower because there was these phonons. Phonons are these lattice vibrations, okay? Which
Okay.
were coupling between that polysilicon and the silicon channel below using this high K material, okay? So you kind of, if you use a metal, you get two advantages. One is that you don't get any depletion in the metal, right? A metal has a depletion rate of
Yes. Mm-hmm.
essentially zero, right? So you don't get any depletion there. And the mobility of the underlying transistors is higher as compared to what you get with a poly gate. So that's why the industry moved from poly to metal gate when I think the first time high K was introduced, right? So that's why the term itself is like high K metal gate. They don't work individually. You need both of them. You can't have just an high K and put a poly gate on.
Okay. Just the extension of it. So correct me if I'm wrong, whether they use two different metals for PMOS gate and NMOS gate in a CMOS?
Yes,
or
they
not?
do. Yes, they do. And you kind of did that in a poly technology by doping your N and P type poly differently. But in a metal gate technology, you use a higher work function material, something like tinitride for PMOS, and you use a lower work function material like something like aluminum based. So it's aluminum that you use for NMOS. Okay. So, yeah, and so you're correct. You're absolutely correct. Okay.
Okay. So this will affect the process even more, right? To do two different metals on PMOS and NMOS. It add difficulties to. So can't they find any metal which is good for both and do some changes in the substrate or something like that?
So you do want your PMOS and NMOS to have slightly different,
threshold voltage.
Yeah, one has to be positive, one has to be negative, right? So the most, the way they currently do it is by choosing a different metal, so choosing a different work function of metal. The other way you could do that would be essentially changing the doping in the channel.
Yeah.
But again, if you already looked at FinFETs videos, we're trying to get rid of doping in the channel rather than introducing it, right? So that would go contradictory to that trend. So okay. So the current way of doing it is having two different metals, but it introduces process complexity, as you can imagine. Like you would have to put one metal on top of NMOS, put another metal on top of PMOS, right? So.
Okay, and I have one more question on EUV lithography.
Yeah.
What do you mean by resistors? That term resistors.
Resistors means like so if you have a resist and if you want to essentially when you expose it, right? When you expose it, and either it becomes hard or it becomes soft, so it can go away when you develop it, right? So when you expose it to the light, right, you can count the number of photons, right, and multiply them with the energy of these individual photons, and you would say this is the dose I kind of exposed it with. And again, Mark over here is a radiologist, right? Mark, you might know this very, very well. That think of, when a radiologist who works in X-rays, right? You always say that, you should limit your exposure. It should not go beyond this particular dose, right? So for this resist to convert from, or it to become hardened, or, for it to change from, have this transformation, you need to have supply a certain dose, right? So you can supply that dose by essentially, these photons which have this energy which converts it, from essentially makes these crosslinks in the resist, and you require a certain dose for that. Okay, so that dose is I think we talked about it in the videos for UV. It's like certain kilojoules per, or millijoules per, not sorry, not millijoules, but it's essentially that amount of energy that's required
Joules
to
per second.
millijoules per centimeter square, right? So it's in that unit. Okay, does that
Yes.
answer?
Yeah, I think so. Yes.
Yeah. Okay. We are almost at the top of the hour here, so I can take one question where wants to like ask one last question. I can take.
I have a question again if nobody has one.
Yeah, go ahead.
So what is this RSIC and x86 and those kind of things, like which is common in the ARM architecture? So what differentiates that from the x86 model, and why does that consume lesser power? Is there an architectural issue there?
Yeah, so one of the things is x86, right? There's this thing called x86 and RISC. Okay, RISC are these ARM are based on RISC kind of architecture, right? So you have a reduced instruction set, right? So again, bear with me. I'm going to go a little Jose, unfortunately, I have to mute Jose again. His voice is adding up. So, if you have a reduced instruction set, right? Like x86, you have a big instruction set, right? So to implement that instruction set, Jose, if you want to post your question in the chat window, I'll answer that. So if you can post it there. Okay. So if you have a bigger instruction set, you need more transistors in your core logic to run it, right? If you have a reduced instruction sets, you need, of course, lot less silicon real estate, or your core arithmetic logic unit, right? It would be much simpler, and the disadvantages of having a reduced instruction set is that you won't be able to optimize your code to at such a large level. If you have more instruction sets, right, your code can leverage that, and instead of like multiplying something plus adding, right, if you have a single instruction which does both multiplication and addition, it would just optimize my code much more. But it would result in x86, which has a larger instruction set, or it has an instruction for pretty much everything. It would result in a microprocessor which has more real estate for this transistor, which does this execute this instruction, versus a RISC which has a reduced instruction set, hence has much simpler silicon piece of silicon supporting that, right?
Okay.
And it translates at higher level. It translates into pipelining and other things as well. So it just becomes, to support that large instruction set and support that flexibility, you just end up consuming, just making your power consumption, it just becomes higher as compared to as compared to like a ARM processor which has a lower instruction set. But if you look at it, it's actually interesting. Like as increasingly mobile devices, they do more and more functions, right? So they do more and more graphics and all. So ARM, it has been increasing in terms of complexity, right? So the power usage in ARM processor, it has been slowly climbing. So if there's an intersect which happens between two, where this is increasingly becoming more complex, and then suddenly x86 is not as complex, or so it's an interesting battle. But currently, just so I guess you can simple way to think of it as like x86 larger instruction set, hence a larger power in the piece of silicon supporting it. Okay,
Okay.
if that makes sense.
Yes.
Okay, all right. Thank you guys for joining on this Sunday afternoon, and have a good weekend, and enjoy the week 4 videos, and good luck for the project. I'm really looking forward to seeing the projects that come out.
Okay, thank you.
Okay,
Thank you.
Thank you.
Thank you very much.
bye.
Bye
Jose,
bye.
sorry,
Bye.
couldn't
Bye
hear
bye.
you this time. Next week. All right, bye.
Bye.